2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello and welcome, everybody. You probably can't see me, but I hope you can hear me. And I'm starting today by showing you again that we have a podcast. So for anybody who is interested in electrochemistry-based humor, which is a very growing field of humor, I heard from myself just now in my own head. Yeah, I encourage you to listen to our electrochemistry podcast, where we've had it out now for a few weeks or a month or something like that, and we're releasing episodes every week or a couple weeks, and we appreciate anybody that's listened or left reviews or anything like that. And yeah, we hope you enjoy it. Anyway, give it a listen. It's pretty funny. It's not super serious. We make dad jokes and movie references and stuff like that. So if you're stuck in the lab doing research and you want to have a good 30-minute listen to us being goofy, fire up the podcast, I suppose.
All right.
I think same time. Yeah, we're conflicting. There we go.
Yeah. Actually, I need to minimize that completely. So welcome everybody to our live stream. Ask Us Anything about electrochemistry. I'm Alex Peroff. This is my colleague, Dr. Neil Spinner. And welcome to another episode. I think we're almost at 40.
I think this is 40 today.
Oh, this is 40?
I think so. Yeah, I think 39 was last week.
That's incredible. So this is an opportunity for you, the audience, on YouTube or on Twitter, to ask us any questions that you have about electrochemistry. And we do get a lot of those, either through YouTube comments or webinars or phone calls, emails, all those things. And sometimes those platforms are not always the best when it comes to answering those types of questions. So we have set up this live stream where we'll go into a little bit more depth on answering your specific questions about electrochemistry. Now, in our time doing this, we have observed that we're not very good at answering extremely specific questions that maybe are very particular to your research, like the activation energy of a very specific molecule or redox species. And similarly, we're not very good at giving you an over-encompassing broad, 5-hour lecture on what is EIS, So what we find is that, or what we have found is that if there is a particular topic in electrochemistry that's somewhere in between those two extremes, we can usually spend between 5 and 15 minutes going into a little bit more detail, talking about those specific subjects. So we are using Restream as the broadcasting platform to put it out there to Twitter and YouTube. And if you are a tier 1 or tier 2 YouTube member in the community chat, you can join us on Restream. You can share your screen, your data. If there's a problem that you want us to look at in more detail, we'd encourage you to do that. We usually run this live stream for about 2 hours, depending on how many questions that we get. And if you are watching this after the live stream, if you can't make it to the live stream, we will have this as a YouTube video that you can watch at any time. And we'll have questions that were asked during this live stream in the description below. So if you are watching this now and you have a question, if you're watching this later after the live stream and you have a question and we're unable to answer it during that live stream, leave a comment and we'll try to answer it in the next upcoming live stream. We apologize in advance if there are any if there are names that we can't pronounce of any people. This is just whatever your Twitter name is or your YouTube profile name is. So we apologize in advance if we have a difficult time pronouncing that. I think those are all the boilerplate things. A couple of things to keep in mind going forward is there's an ACS meeting next month in March that Neil and I will be at. That's in New Orleans. So if you're attending the ACS meeting, you should stop by the Pine Research booth, have a chance to meet us. We'd love to talk to you. There's also, we have workshops that are coming up. More webinars will be coming up in the future. Doing a thing at Case Western, and there'll be more like talks and stuff. So follow us on Twitter and YouTube and other social media platforms, LinkedIn as well, and that way you can know when some of these events and things are going to be happening in the future. I think that's about it.
It's a lot of boilerplate.
It's a lot of boilerplate. It
right.
always changes a little.
Every
bit.
time that you're not here and I have to do all of that, I get a mild panic attack. And I'm like, I don't remember all the things. What does Alex always say? It's just better when you do it, because then I could just sit here and just kind of, yep, those are all the things.
Those are all the things.
All the different things I'm supposed to say. These are the types of questions you should ask.
Yeah.
These are the kinds of questions you shouldn't ask. Yeah.
Well, we've only learned that later after
that's
doing
an experience.
That's an experience
sure.
thing.
Yeah.
That
If you listen to, if you go back and listen to some of the first episodes, it's funny how we've even changed a little since episode 2, 3, 4, or whatever it is.
Oh yeah.
The style a little bit, and also, the way it was handled. I guess it's to a certain extent about the same. I mean, we just get your questions and we just try to answer them as best we can. But the the flow, I think, has gotten more smooth. We kind of, you kind of get used to doing this once you've done it for a while.
Yeah. You have a system. We usually have a system in place. Right now, we don't have any questions right now, but we can wait around it, for a bit. I have been looking at some electrochem. So actually, during the last live stream, someone was asking about DPV, and I couldn't, I don't know enough about pulse techniques, so I ended up spending a lot of time reading this book, which is Electrochemical Methods, Fundamentals and Applications. You probably can't see it.
Never heard of it.
Here. It's Bard and Faulkner's book. And actually, it's been a while since I've read it. It's actually pretty good. There's a lot of math. It's super detailed. And but if you actually just accept the math for what it is, and then you go to okay, that's the important equation, it usually has some pretty good descriptions of electrochemical processes and things to keep in mind. But it is a difficult it is definitely a difficult book sometimes if you're
it's
novice.
A dense book, because it's like, it's a college textbook basically, right? So it's got plenty of that
like
light
graduate school textbook.
Well, yeah, it's exactly.
Yeah,
so it's even
level.
more so than that, and it's got enough of the example problems and whatever, like your homework is do numbers.
Yes.
One, it's got
problem sets in it.
Problem sets in it. Yeah, exactly. So it's got all of that kind of stuff in it. But it's like if you're just reading it casually to learn, you don't have to do all those kinds of problems. But I think it does become difficult for some folks in some cases, because the mathematical derivations become sort of like your eyes glaze over, like you don't really understand what you're looking at, and it's kind of like, I just kind of want to know, especially like DPV, you're trying to learn. There's a lot to DPV, right? There's the math behind the whole thing. Okay, that's one part of it, and then there's the phenomena behind what's happening.
Yes,
and then it's just like the description of those phenomena can be convoluted. Is it the math of what happens at the top of the pulse versus the bottom? And then, or is it? I think that's kind of another one of the reasons why we've been trying to do these live streams, to be honest, is because it's like in this what I would say the downside and the upside.
Mhm.
I'll word it that way. Is
Of the
that like
pulse.
we don't have I don't mean the pulse. I mean
That side of the
yeah,
pulse. I had
the
to say
down
that.
pulse. Yeah, the downside is that like right now you and I are not like perfectly well. Maybe you are, but I don't feel like I'm perfectly well equipped to like do heavy mathematical derivations.
I'm
If
not.
someone has a question about square wave voltammetry, I know about it. I could say some things about it, but I'm not going to be able to be that like mathematically deriving everything in front of you. And probably that's not what you're asking and looking for if you're asking a question about that now. But the plus side is that we can probably share practical things,
Yeah.
you know, that you may not get in a textbook, for example, where, you know, it's like the textbook is going to give you mostly the theoretical, mathematical, whatever. Whereas in a setting like this, we have more of a capacity to say things like, well, you know, you're going to have to adjust these parameters this way, and you know,
Yeah.
and experience says that this is probably a good range for that number to be. And, you know,
Yeah.
those are the things that I think are missing in a lot of textbook.
Oh yeah, absolutely.
You know,
Absolutely.
it's hard to get a practical beginner, you know, crash course on
Mhm.
like doing experimental electrochemistry.
Oh yeah. And even some of the books that talk about the practical applications of doing experiments, like, okay, this is what you do, this is what you do. Until you like someone kind of guides you or you've seen it, you really don't have any idea. Like you need to experience it. You need to do the experiment
Yeah.
to really understand it. To
Yeah.
do it.
I think I answer that question that way a lot of times. I always feel badly. It feels like a sad answer to, you know, if someone's like, well, how do I XYZ, right? And it's
Yeah.
like, get into the lab and do it.
Well,
And
yeah.
it's such an unsatisfying answer because it's like if someone has the like you know, the courage, I suppose,
Mhm.
to ask like, well, how ought I to do this, or how does this technique work, or what should I do? It's like, you know, I applaud anybody who seeks
Mhm.
knowledge and
Oh
seeks
yeah.
wisdom.
Yeah.
Like those are good things, obviously, you know.
Mhm.
But unfortunately, a lot of times the answer to those kinds of questions is it is experience. There's no substitute, you
Yeah.
know, for the experience. Like as an example, like one of the ones that I always like peel back the curtain here. One of the ones I always hate getting in our
Mhm.
job, like when we're, you know, helping customers and troubleshooting things or doing what have you. One of the ones I hate the most. It's not because it's a bad question.
Mhm.
Is when people are doing oxygen reduction and you don't
Yeah.
get your S curve doesn't look perfect
Yeah.
when it doesn't flatten. You know, at the oxygen reduction, the diffusion limited. You know, maybe it's curving down or whatever. It's like,
Yeah.
how do I get that to be flat?
Oh yeah.
It's like
Yeah.
I hate that question because honestly, I don't 100% like I have, you know, a handful of things that I know that can help. Like there's a lot of, you know, suggestions
Mhm.
and little techniques that I try to share in that case. But it's like the ultimate reason is a lot of the times like keep doing it for 2 more months and you might be better at it. Like it's just hard,
Yeah.
right? A
Yeah.
lot of times that's the answer. And it's just like that's such an unsatisfying answer. And it feels like a cop out, you know, it feels like I'm not
Yeah.
answering or, you know, it feels like we're not giving a valid answer. And it's like, but that just is the answer. You'll figure out kind of like how to do it better if you just do it,
Yeah. Yeah.
you know?
Yeah, there is yeah, there's definitely something to be said about that. We can give them some troubleshooting tips
Mm.
while they're doing it. Tips are always good.
Oh, for sure. Yeah.
All right. So we have our question. First question from
Santiago.
Santiago. Hi, how is the standard reduction potential determined? What is the technique or process used?
It's Gibbs free energy, right?
Well, yeah,
Basically.
yeah.
Like-
There are many ways to actually determine the standard reduction potential. I would say the kind of the easiest, and when we say standard redox potential, I think we're talking about E naught, at least in textbooks and things like that.
Mhm.
I'd say one of the best ways to determine it is cyclic voltammetry. That's one of the ways, at least. So,
Oh, I guess, yeah, I interpreted it way differently than you. I interpreted it as like a first principles.
that's the first
If you're
principles.
talking, yeah, you're there. Yeah. So the two possible answers,
Mhm.
one of them is what Alex is probably going to show you, which is more like practically, how would you find
Yeah,
what that is, which you could probably do with the simulation software in a
yeah,
second
yeah.
here. My answer is much more basic, which would be, I'll just draw this really quickly here.
Yeah,
This
yeah,
is
go
just a
for it.
simple kind of a thing. But basically, if, and again, maybe this isn't what you're asking, but right, delta G
Mhm.
is minus NFE, right? This is like
Yeah.
definition. So in some sense, the like technical definitional answer to your question, E0, I don't know if you, sometimes the E0 is up. I never know whether to draw it up or top. You know, is the zero supposed to be the bottom or the top?
Oh yeah.
I never, it's like one of my weird things. I never know which one to do.
I always do top
It's the top.
right. I think.
It's a superscript or a
I
subscript.
think it's a
For some reason, it's one of
superscript.
those things. It's like the equation
Yeah.
for capacitance and scan rate. I
Oh
lack
yeah.
I
yeah.
lack whatever like chromosome is required to retain that information. I know it's not a chromosome. I
Yeah.
can't remember for some reason. Anyway,
Mhm.
so this answer to your question, which is much more fundamental,
Mhm.
is that it's actually just solving this equation for delta E. So if you have your reduction is, you know, A plus an electron goes to B, whatever. That standard E0 is getting the delta G is like G of B, right? The delta G of B minus the delta G of A, you know, whatever. The Gibbs free energy, maybe these shouldn't be delta, whatever. You know what I'm trying to equals delta G. So basically, you're finding the change in Gibbs free energy of the products minus reactants. That's delta G of the redox, and then the number of electrons, which is here, and times Faraday's constant. So you just delta G over NF
Mhm.
is yours. That's how you get your standard potential. So that's just mathematically like
Mm.
first principles how that works. But Alex can show a thing about practically if that's what your question is.
Yeah. So one way of calculating it electrochemically is so I'm going to use a simulation software called Aftermath Live, which you can go to our website and actually look at it. It's a subscription model, but basically, if I have a let's do just like a reduction reaction. Let's say the E naught, and actually, I guess the answer is E. It's in the upper right hand corner because it's on our software.
Oh, is it upper right? Okay,
It
so
looks
I
like
wrote
it's
it
upper right here.
Okay, good. I guessed correctly.
So if I simulate it, there's always been questions like, okay,
Oh, good. So just to clarify, Santiago did clarify here.
oh,
I was referring to what technique and how the numerical value of the experimental result. So it says what you're doing now.
yeah.
So my explanation was not what you were asking, but I hope that it was excellent anyway.
Yeah.
Please continue.
So, but basically, you can get the information from cyclic voltammetry. Now, if you have a very, very perfect cyclic voltammogram, the E1 half, so the half potential between these two peaks, would give you the value. Additionally, technically more, it's like, I think it's like 0.7% up the like anodic or the anodic, and then 0.7% down the cathodic.
Yeah, it's
Is also it. But really, what it comes down to is it's at this point right here. So actually, if I actually animate this, and maybe I can get it to stop at the right point, which is I'm watching surface concentration. Okay.
oh, they're just equal. So close.
Just so close, so close. I can maybe.
It's like one of those games at like the arcade where you have to like
Yeah.
slap the light when it stops at the, you know what I mean? The
Yes.
100 points or whatever. Anybody know what I'm talking about? Anybody? Sorry.
But this point, like the potential. Oh, I've made my voltammogram a little bit small. This potential, like basically right here. So it's not actually at like E0 in a way. It's right here when the concentration of both the oxidized and reduced species are equal to each other. That is when the potential is equal to E naught. And so it actually happens twice in this case. Now, one thing that is important to note is that you can get deviations in what the standard redox potential is on your, because if you're using your CV to determine the standard redox potential, you can get deviations if your heterogeneous rate constant here, K, is different. Also, if the diffusion coefficient between A and B is different, which most of the time it's not, but if these two things are different, the E naught is gonna shift, and you can't necessarily use the halfway point. So if I made this like 4, you're gonna notice that when I simulate it, it actually moves it away. You'll actually notice that this shifted to the left a little bit. And if I made this 6, so these are getting kind of farther apart. If I simulate, it's shifting more away from the E naught value, which is 0. So we know what E naught is. So if this condition, but if these are the same, like if these are both 1 times 10 to the minus 4, if you simulate it, you will get like, oh, the E1/2 is halfway between these two. So that's another thing to consider when calculating and determining the E naught. And the other thing is the reason why the E naught is equal to the point where the concentration is equal between the oxidized and reduced species comes from the Nernst equation. And basically it's let me also just share again. Where is my, here we go. Let's see. There we go. So let's see, can everybody see? Yeah. So just to show everybody my favorite equation of all time.
It's the Nernst equation.
The Nernst equation. The potential that you measure is equal to E naught. And that's like minus, I think it's like, it can be plus or minus, but it's like NF. I think I'm getting this confused with like what goes on the top and the bottom. I think it's NF over RT. But the important thing, I'm messing this up, is that you have the natural log of the reduced and oxidized species. These brackets are just terrible.
Listen, if your artistic skills are bad, then I don't know what that says about mine, because mine are worse. That's what it says about them, I guess.
I think it's NF over RT.
NF over RT.
Over RT. Yeah. That's right.
So it's your favorite equation.
It's my
How
favorite
can
equation.
you not know?
I know. I feel very bad about.
No, it's
myself.
RT over NF.
Oh, okay. Yeah, I figured something was.
It's like
something was not right here.
I just had to Google it, so I cheated.
Thank you. But we got the right. We got the right.
Yeah.
So
the natural log is the part that matters here.
RT over NF.
Yeah.
And it's so another thing that's very important about the Nernst equation is this only happens at equilibrium. Okay, so this only happens at equilibrium, and when and if it's at equilibrium and the concentration of these two species are equal to one another, then this whole thing cancels out, because you have the natural log of 1, which is 0, and then your potential that you measure is equal to your E naught. So that is how you're able to determine the E naught, the standard potential for systems. Now, this also gets complicated if you have irreversible systems. So if you have more complex systems that are not just a very fast electron transfer, then it might not work so well. So we can talk more about that, but I know that there's some other questions that are coming up. Hopefully, Santiago, that was helpful.
Adam has a question. I'm not a tier 2 or tier 1 member. Am I able to post screenshots of my aftermath window to show the troubleshooting issues I've had? I don't think so. I don't think that works. For two things. The first is that I don't think on YouTube in a comment you can post an image. I don't believe that's possible.
Yeah, no,
right?
You can't post
and then the second is that we're streaming to YouTube, but we're using a secondary platform called Restream. You can probably see in the upper right corner of your screen, it says Restream. So basically Restream is the hosting. It's called encoder, right? I guess.
Yeah.
Basically it's the where we're actually streaming, and it's connecting to YouTube and to Twitter simultaneously, casting it there. So the long and short is that the answer to your question's basically no, unfortunately. So if you have some visual stuff that you want us to see, you have basically two options. You can quickly join on our YouTube channel, which I understand if you prefer not to, that's totally fine. Or you can email us images, screenshot. We can handle through email, and then from email, if you would prefer to have a video session where we can talk one-on-one, we can set that up offline separately. Like we can set up a like a video meeting with you if you have some issues you'd like to troubleshoot, and it's easier to talk through them with us. So if you aren't able, as I said, to join like now over the next 30 to 60 minutes
Mhm.
and join us live here, please send us an email with your images, and we'll either handle them through email or we'll set up a video session with you. I'll type our email
Mhm.
Into the chat right now. So that's our sort of sales email that we can all access.
Mhm.
And yeah, if you have any of that, please send us an email there, and we'll certainly be able to help you. And then next, I think I have some. I can answer this here. Mahesh has a question. What is the right region to take Tafel slope if plotted from LSV data? I feel like this question pops up all the time.
Oh yeah. Well,
The
Tafel slopes.
Tafel slope is like the
it's
most
always,
popular, one of
it's
the most
always
popular, frequently used
techniques.
electrochemistry techniques for sure. I
it's
I understand why it's ubiquitous. It's in so many publications.
Yeah.
And so the short answer to your question is wherever there is kinetic information, and only kinetic information. So the implication of what I just said is that if you're doing a simple LSV and you don't know, or you do know, for example, that it's just some 3 electrode system, and you have
Mhm.
a lot of things happening when you do an LSV or a CV. There's kinetics, and there's mass transport, and there's double layer capacitance, and there's side reactions, and there's electrolyte decomposition, and there's little gremlins running around your electrode, sending electrons here and there. That one's definitely happening. The point is, there's a lot of things happening, and it's not just kinetics. And so it is. So I want to clarify before I kind of show you some Tafel plots and some practicality of this, is that it is entirely possible you should not be making a Tafel plot from your LSV data. I want to clarify that, because it's like one of my pet peeves and crusades now with electrochemistry, it seems, is that people are very frequently making Tafel plots inappropriately. The Tafel equation, I'm not going to show the derivation of the Tafel equation right now, unless you have a question about that specifically. I'm going to show you a Tafel plot and try to answer your question. But the Tafel equation is derived directly from the Butler-Volmer equation, which is my favorite equation, unlike the Nernst equation, because the Butler-Volmer equation is a description of kinetic current only. It is, which is like, in some sense, ridiculous, because nothing's ever like purely kinetic, or it's hard to do that, right? But that's why we have methods like rotating electrodes and Kentucky Levich analyses and things like that help isolate kinetics from mass transport, etc. Okay. Now let me try to walk you through a little bit of that, if you do have the ability to get kinetic information. Okay. So I'll bring up our software here. So let's say you have some data like this, like rotating disk or rotating ring disk data, okay, which is normally where you would be doing an LSV and getting for transformations for Tafel analyses. So the kind of data that you're looking at here is where there's a reduction, and so this is where this curve starts going down. Let me adjust the axis a little. Right, this starts decreasing. That's where kinetics starts taking over. The Butler-Volmer equation would loosely describe this curve at the beginning part of it, and then it makes this sort of S shape, right, and kind of flattens out. That's where you have mass transport limitations, and that's where you'd have like Levich analysis and diffusion limited currents. So in brief, if you have a situation like this where you have rotating electrodes and you can isolate things like kinetics and diffusion, the kinetic region is usually very loosely aimed at this part here, the curve part, and the part where the current is rapidly dropping. Basically, it's not the very beginning part, and it's not the very end part. It's kind of everything in between. Sometimes it's called the transition region, or a mixed region. So it's like mixed kinetic, mass transport kind of information like that. So that's the visual sort of rough answer to where you would choose on a rotating curve, for example, to um, isolate your which potentials to do Tafel analysis. Now, I'll jump to the sort of conclusion, which is of an actual Tafel plot. So this is a Tafel plot. I kind of skipped some steps. I did Kentucky-Levich analysis. I extracted from these curves the kinetic current only using Kentucky-Levich analysis, and I plotted. I think it's down here. It says current, but it's actually the log of the current. I just had to pick a unit, so pardon the the units aren't exactly accurate. But the most important thing is that the potential here is on the y-axis. Is a Tafel plot, right? It's potential versus log of current, so it's like millivolts per decade, right? Millivolts is y per decade of current is on x. So when I do a baseline, which is basically this is the Tafel slope. So the unit, forget the unit shows ohms. Don't worry about that. That's just the software thinking that this is current. It's actually, it should be millivolts per decade. So forget about the unit. The point is that the other kind of way people, researchers often tend to find what the potential window for their Tafel slope should be is that it's like a backing out of the Tafel analysis what Tafel slope I want. So for example, if I say to myself, I know about the mechanism and the kinetics of my experiment, my what's going on, that it's one electron, it's perfectly symmetrical, perfectly irreversible, etc. I should have 120 millivolts per decade. That's like the ideal Tafel slope for a one electron transfer process, right? Then what I've just done here, coincidentally exactly 120, is found the limits where my slope is 120, and then what I'm sort of doing here as a it's like reverse order kind of. I'm finding where it's like instead of saying this is the voltage range, what's my slope, I'm saying this is the slope that I know should be, I don't know, this is the slope that it should be for my process. What's the voltage range of where that slope is 120? And so in that case, what I have here is, you can see at the top here, this is wherever I'm hovering is where the voltage is. So this is like minus 160 millivolts to minus 220, 210. So that is also a way to answer that question. I get the slope that I want, that I think is accurate. And then what are the voltage limits on the y-axis here, where that slope is what I'm after. And so that would be another way to say, well, this is the kinetic region between this potential and this potential is the kinetic region where my slope is accurate. Now, again, I just want to end with the important thing that I keep harping on all the time, and apologies for being a broken record. But if you have just a regular LSV on some stationary electrodes and you make a Tafel plot and you do just what I said and you find where the slope is, whatever, and you say that is, there's my kinetic information, you have not applied that properly. And your Tafel slope is likely meaningless because the current on your Tafel plot must be kinetic current or it isn't appropriately applied. You're applying an equation that does not describe the data you're using fundamentally. So it's an inappropriate application. Now, I know a lot of people do that in the literature anyway. They just turn their LSVs into Tafel plots and they draw all kinds of crazy conclusions from them. And fine, I know that's a practice that's done. I disagree with it, but it's sort of how things are done. I can't change the state of research, but fundamentally it's inappropriate and it's incorrect. So if you are able to isolate kinetic current and make your Tafel plot, those are some suggestions I have for you.
Yeah. I'm just thinking about because usually when people do like LSV to do Tafel plots, they need to go like very, very slow scan rates.
Yeah,
Very slow.
So you have not a appreciable amount of capacitive buildup.
Yeah.
From a fast scan rate or whatever.
Yeah, and it's an estimation, because you will have some capacitance even at like 1 millivolt per second or something, but you're hoping, I think, that it's like super, super minimal.
Yeah.
And I guess thinking about it, because usually like when they go over like Tafel in like the book, it's like you have like your E0 and then it goes like outwards from like the over potential from that point. So
Mm.
the over potential needs to be driving the reaction to occur. And ideally, like if you had just like a simple one electron transfer process, like with ruthenium hexamine, like in the Tafel plot that you had, the slope was basically the same for the vast majority of that like potential window.
Yeah.
And only once you go to a potential range where something else is happening, well, then you have multiple electron transfers and your slope changes. So that is also an important thing to think about and consider when like, well, what region do you take the Tafel slope? Well, it's the region where a specific electron transfer process is happening. And when you move to another region, other electron transfer processes may be happening. So think about that and keep that in mind as well while you're doing it. And luckily, you didn't have to scan like way out to like hydrogen evolution region and
Yeah.
get like all kinds of other electron
Yeah,
transfers,
that's
because then your
gonna-
slope would be off.
That would convolute everything even more.
Yeah.
Because that's another thing is that, again, if I'm just on my soapbox of
Yeah.
broken assumptions involved with the use of the Tafel, the other odd assumption built into the Tafel analysis is that it's supposed to be, which flies in the face of the fact that there's an N in the Tafel slope.
Mhm.
It's sort of, I think it's implied that it's supposed to be like a one electron irreversible process. Like that's
how it's defined.
Yeah, like that's how like the Butler-Volmer equation is defined. It's like right, if you have
O plus electron equals R.
Yeah,
That's where it starts
it's
from.
defined from that exactly. And it's like, so when you have more than one electron transferred, it kind of is like, even that is like kind of fundamentally
Convoluted.
Yeah, it's
Yeah.
like, and you've described this well before, where I think that the rationale is that only one of those electron transfers is quote unquote slow and the rest are fast.
Yeah.
So that you've described that before, I
think
think,
yeah.
right? Effectively, it's like if you have 4 electrons transferred, the second one's really slow and the other 3 are fast. So it's like it still roughly follows that it's kind of like one electron from
yeah.
a speed perspective, but you can still measure 4, something like that.
Yeah.
I'm paraphrasing, and I might not be exactly right on the
Yeah,
description.
there's like I think I remember talking to Dan Shearson about this, because it's like because there's a lot of there's like fundamental reactions,
Yeah.
and then there's like the sum of those, and if the sum of those can be simplified into like something like, oh, it's just a 4 electron transfer process, then you might be able to maybe use some of the same.
I mean, that's what's done with
approximation.
oxygen reduction reaction all
Yeah.
the time, right? Like when you have your platinum on carbon, or your platinum on ruthenium and palladium on whatever the hell you're doing, all of that kind of stuff that people are doing in literature all the time to study oxygen reduction reaction. One of the main things that people do is to determine the number of electrons transferred using Levich analysis, and you're trying to get it as close to 4 as possible, because the oxygen reduction reaction in theory has 4 electrons transferred, and if it has 2 electrons transferred, you're making peroxide, which is a poison, and it's bad, and whatever, right? Like that's one of those fundamental like fuel cell RDE kinds of fields of research, and so it's like that whole analysis is predicated on everything you just said, which is that your ability to like group it as a 4 electron thing based on those reasons. It's not, I don't disagree necessarily with it. It's just that it is something to be aware of as a researcher and as a scientist, that you want to know what you're using instead of just using it blindly. Having a little bit of a higher knowledge of it or something is wise, right? Because that to me is less egregious than just taking any CV and making a Tafel plot. Like,
absolutely.
Assuming the speed of certain electron transfers and being able to lump it together to get an estimate for N is at least reasonable, because it's still kinetic. It's all kinetic. Now we're just talking about the rate of kinetics, and it's like if you had a process that in theory had, some sluggish kinetics for some, or whatever, maybe you'd get some wonky analyses, but it's still all kinetic. It's like, just take people. This is again why I harp on this all the time, because it's like, if I can do anything to just sort of spread any education about this, I want to, because it's very pervasive. I answered a question on our YouTube channel. Someone left a comment on maybe our last live stream or something like that, just last week or the week before, asking about like basically I think their question, it was a good question. It was like, why do I see so many Tafel plots in everyone's research everywhere? And it's like one of two things. They're either doing a lot of really good kinetic studies or everyone's doing it wrong.
Yeah.
And I don't appreciate that. I'm not saying I do everything right either. I'm just saying this one particular case, it's like you can't just take a CV and just make a Tafel plot out of it. I mean, you can physically do that. It doesn't mean anything though. I can take my CV data and just take the, square root of the y-axis and the, natural log plus, the multiplication of them on the x-axis, and that also doesn't mean anything. Like you're not doing anything. You're just manipulating the data and the axes and assuming you're getting something out of it. You're not. It's not kinetic information. Like it's meaningless.
Yeah.
So I bristle at that for a good reason. I don't want to have people, making broad conclusions about their data on mistaken analysis. It bothers me, as you can tell.
As I can tell.
Yeah. So.
All right.
Anyway.
Okay. All right. So Santiago has a follow-up question, which is previously explained to me how to observe the decomposition of the electrolyte from CV. Can it also be observed for GCD?
Yeah.
Galvanic charge
Yeah.
discharge?
Sometimes not quite as obviously as CV. I don't know if I drew it or Alex drew it, but you'll see some, if the electrolyte is being decomposed, like the most common examples are oxygen evolution and hydrogen evolution reactions, which happen at the extreme potential windows, for example, in water. So this might not be perfectly analogous to GCD, which would be like non-aqueous electrolyte for a battery or something like that. That being said, the decomposition of electrolyte usually happens at the extreme potential windows in a CV, and sometimes is accompanied with noisy, craziness because the electrolytes kind of get ripped apart and you get gas bubbles and stuff like that.
Mhm.
So in CV, it is all obvious. In galvanostatic charge discharge, it's not always so obvious. One example is the solid electrolyte interface, the SEI. So for example, in a battery, when you charge discharge for the first time, you'll get something like this. That's the charging curve. And then the discharging curve might be whatever. So I don't know, and then so this is like number one. And then number two and beyond will be this. Right. And so you have this big difference between charges 1 and 2. And that's electrolyte decomposition. But it's specifically SEI formation, solid electrolyte interface. So the quick answer to your question is like an extended plateau. If you're doing battery GCD, you might get a really extended plateau that indicates formation of the SEI. If it didn't exist previously, you'll have a long kind of lag while the SEI is happening. And the SEI, it's tricky, right? Because technically the SEI is electrolyte decomposition, but it's also a beneficial electrolyte decomposition. And it's necessary for battery operation to have the SEI form primarily on the anode. If you have a situation where your catalyst is just ripping the electrolyte apart in a bad way and it's beyond SEI, probably what you end up seeing is like you're trying to charge your battery and it just hangs. Right? It should, eventually go up to your upper limit on your voltage, and it just kind of hangs either when you're trying to go up or you're going down. Like it'll just hang forever at one voltage. That is usually an indication, and like, I'm talking well beyond, like you make your battery with something and that whether this is time or capacity, you say to yourself, okay, I put 10 milligrams of carbon, and so I know it should last. This is the C rate, this is the rate of discharge. Like if you are a battery scientist, for example, or a supercapacitor, whatever, you might have a rough idea that like, okay, this should last an hour or 2 hours, or like you have some idea of about how much time it should take, and it's it's been like 5 hours and it's still just hanging here. It's like, that's just ripping electrolyte apart. There's no other reaction to be happening. And so something is wrong. Like you either made the battery improperly, the SCI didn't form well, something has gone wrong. The battery should be stopped and taken apart. Like something is not right. This is not a, that is a battery gone bad, or it was never good to begin with. I've had this happen to me a million times. Like when I was learning how to make coin cells, and sometimes I didn't make them well, or the material I was working with didn't operate properly, or like I didn't put enough active material on it, and so I just had like the current collector ripping electrolyte apart, and it, you're waiting for it to charge up, it never does. So that would be my answer visually for what you might see from a galvanostatic charge discharge, if you're just having this electrolyte ripping apart and it's not really doing what it's supposed to do. So give that a try. Give that a look or whatever, if that's what you have going on.
All right.
Looks like there's a bunch of other stuff you're handling now. I know.
Yeah, just quick thing. I told Mahesh that Batsol is our distributor in India. So if you want to buy Pine Research equipment in India, Batsol, should put that there. Going down the list, Adam, he may continue to talk to us later about his question, but he says he's running into an issue when he takes CV for CO2 reduction. The CV will cut off when I go to the more cathodic potentials. This is not a consequence of making the current range too small. So a little bit of a follow-up is it not going to the correct potential? Like you say, oh, go to -3 volts, and it never reaches -3 volts. It's maybe only reaching -2 or something like that. Or is it like the current is actually getting cut off? Because I think you're right that if the current range is too small, then you'll get a flat line with the current. But you're saying that the CV will cut off. So I want to know exactly what cut off refers to. Is it the potential, or is it the current range?
Because it could be a compliance voltage issue if it's if the potential is not getting where it's supposed to. And you'll see this sometimes where it's like the voltage is scanning and then it like hangs, it can't get there. It could be a compliance voltage issue. Could be a connection. Could be a connection issue. It could be that a bubble is forming on one of the electrodes. You're doing CO2 reduction. There might be some sort of bubble
CO2
forming
around.
or CO2 bubble. Something is breaking up the interface, and it's temporarily causing a tremendous resistance because the electrolyte interface is interrupted, and that is in turn causing a compliance voltage issue, a connection issue, something like that. And the potentiostat is not able to apply and measure the potential you've told it to. So please clarify, I guess, if you want, but that's kind of the short answer as to what might likely be the cause of something like that. But also, again, as Alex said too, email us and show us the images and share if you're using Aftermath, as I think you said you're using, it's an Aftermath thing, so you can share the archive file with us directly. We can look at the raw data. That might help.
Yeah. One thing you can look at is the potential waveform that's being applied. So what you're trying to do is apply this.
It's called the excitation waveform.
Excitation waveform.
Just in Aftermath, if you're doing it on the other plots, look at excitation waveform. You'll find what Alex is drawing right now.
So this is like this is what you told the potentiostat to do. You want it to go from this potential to this potential back, from one to the other. But what you'll find is that when the experiment actually occurs, it'll trace as much as it possibly can. I'm going to use a different color, slightly different, so you can see. It'll try to, it'll reach it, and then all of a sudden it goes flat, right? And then this will be your compliance fault. It's like it's not able to get past that range, and then if you kept it going, it'll eventually go back. It'll start to, it's going back again. So if you observe this, that's a very good indicator that you have a compliance voltage issue. So something to think about and keep in mind while you're troubleshooting.
Yeah.
All right, let's look. There were a couple other questions.
Yeah, Dooley's has a question.
Yes.
So you have access to a legacy, you clarify, AF-ASR. So the old ASR rotators, the rotator before the MSR, which is our current longest standing, I guess, popular rotator. You learn that you have to replace the shaft for the instrument. Is there a kind of student discount so I can buy and run DAT RDE experiment?
That RDE
Yeah,
experiment.
DAT RDE experiment.
Yeah.
So first of all, we still sell shafts. We don't sell the ASR rotator anymore, and we generally try to support our products for their lifetime. But it is a legacy discontinued product, right? As you noted. But we do sell. We can make the shafts for the ASR and sell them.
Yeah.
What's the AF? What's the part number for the ASR shaft? It's been forever.
I'm trying to look. We would need to know a little bit more
Yeah.
details about like.
I think
I'm trying to see if on our
can't-
website if there's.
I can't remember.
I don't have access.
AFE 5A or AFE 6A, something like that. I think it's AFE
Oh, yeah.
6A would be like if you have like 15 millimeter or 12 millimeter.
Yeah, you're right.
It's AFE. It has an A in it for ASR. Basically, our website's having issues at the moment. But anyway,
Yeah.
it's AFE 3A or AFE 6A or 5A, something like that.
Yeah.
So that would be the part number, I think. Anyway, to
Yeah.
the other part of your question, is there a student? So it depends where you are in the world, right? If you're in the US, we have a standard, academic discount that we offer. It depends, again, if you're in the US and you can contact us, we can get you a quotation directly. If you're, depending on which country you're in, we have exclusive representatives, for Europe, for China, for Asia, for different parts of, not all of Asia, but different countries in Asia and in Europe, and et cetera. So the answer to that part of your question is it depends where you're located, because we have a series of international distributors around the world, and so contact us probably by email, and we can determine that for you, whether we can send you a quote or we have to refer you to one of our distributors. But most likely we can help you, get a new shaft for the rotator.
Yeah,
for sure.
There's a question from Taufik, I think. And I looked a little bit at this. I don't quite know all about it, but it says for a cell, the the efficiency is defined as delta G over delta H. Also, delta G is equal to delta H minus T delta S. So the process when the entropy delta S is less than 0 and delta H is greater than 0, minus T delta S is greater than 0. Notice the negative sign. Hence, delta G is greater than delta H. He mentions a few things later. And then he's asked, and hence delta G. So right now there's no question here.
Is there a question here? I'm trying to think.
But I don't know if what you're trying to do or figure out is why, I think he's trying to figure out why does he have an efficiency that's greater than 1 for if delta G is greater than delta H. I think there are some. So first off, I don't know. I've never heard of thermodynamical efficiency or thermodynamic efficiency defined by delta H over delta G over delta H. I've never heard of that. And you can even, if you look at the equation, I mean, this efficiency, what does that refer to? I mean, there's thermal efficiency that has to do with work and heat in like an engine. That's like a different kind of thing or a different kind of process. But looking at some of these things, when you have a positive delta G, your process is not spontaneous. It requires additional energy. It has no free energy, or it has a high positive free energy. And if delta H is also positive, then that also means that energy is required for the system. So there's a lot of questions about these equations and what they refer to and what they mean. And remember, these are all systems that are at equilibrium, right? All this stuff applies to things that are at equilibrium. So, it's a little.
It just seems like I'm just sort of fundamentally confused, because it looks like that you've put this question kind of either twice identically, and then above, it looks like you sort of you stated the stuff with both possibilities, right? Where you have positive entropy and negative enthalpy, and one where you have the opposite, negative entropy and positive enthalpy. I guess I just don't know what the question is. I don't understand what the question is. So, I mean, like Alex was just saying, it's like, right, if your enthalpy or your delta H is one way or the other, it means you require energy for to run or that it produces. It's like an endothermic versus exothermic, and then entropy being positive or negative describes whether it's,
Yeah.
Not spontaneous, but because that's what delta G does. But whether it's more ordered or less disordered, the entropic whatever properties of the reaction. I guess I don't understand. I mean,
Also, you can also
understand what
like
the
you can
question
get
is. What's the
this
question?
delta G, right? So you're saying that the
Yeah.
efficiency is equal to
Is greater
delta
than
G
one.
over delta H. Oh, did they write anything?
No, I don't. Yeah.
So you can get that from the other side if you divide both sides of the equation by delta H, so that you have like delta H times like 1 minus T delta S. You can actually solve for that equation with the formula. Let's see.
Yeah, if you divide both sides by delta H, you get 1 minus T delta S over delta H.
Yeah, and it's
Which
like,
I get whatever that
and
is.
then that's equal to the efficiency. So it's it's kind of a weird it's a weird thing. And the other thing, I just don't know if that's, and then actually what you should look for is what is a condition when E is greater than 1. Can you get a situation where T delta S is greater than 1? And it's like, okay, well, maybe not, but I think there's some first off, we need to know what the question is.
Yeah.
Like how can you
Yeah,
have
I
a
don't-
thermodynamical efficiency that's greater than 1?
Is that the question?
Is that the question?
Or is it you just sort of having an interesting discussion about this sort of thermodynamic, definition, which is interesting. But I mean, I guess I don't understand what the exact question is here. So let's just leave it there for now.
Yeah.
And if you have a follow up, Tawfiq, you can type it in because we're not sure exactly what your inquiry is about here. So
yes,
looks like there's another question. Yeah, there was some interesting stuff about our Indian distributor. So yeah, please contact Batsol if you are in India and you need a quotation or some discussions about getting our products. Batsol is in Mumbai and Kolkata. They have offices on both sides of the country, so they can easily help you out.
So we have a question from Liza. We had this question before a while ago. If I want to measure the diffusion coefficient using the Levich equation that you used in a video, can I do it with current density versus rotation graph, or is it only valid for current? So the Levich equation is only valid for current because the area is in the Levich equation. So you could divide.
Let me pull it up.
You could divide both sides of the equation by the area. So you just have to make an adjustment in when doing the math. So
Levich.
Yeah, we can.
Yeah, I'll pull it up.
Bring up the Levich equation.
It's actually it's irrelevant. I don't mean that to trivialize your question. What I mean is that yes, you can do it with current density. You just have to know what equation to use. That's all. So the Levich equation, which one of these is it? This one. So this is from might be what you were referring to. This was my webinar I did on Levich, Kentucky Levich, everything. So this is the Levich equation, right? So basically when you rearrange it to get the expression for D, you get all this. So instead, all you do is just divide both sides by A. So that would go away. And this would become current density. I'll just put J here, whatever, right? So all I did was take the A that used to be over here and divide it over here. And now I put J because sometimes we use J for current density. Now this is the same equation. It's just in terms of current density instead of current. And so when I do my D, I would just get rid of the A in there. So that's it. That's all it is. That's literally all the only difference you would make is that you would solve this expression with A divided on both sides and over here. So absolutely, you can do that. Just make sure you're using the proper equation. You don't want to have area multiplied in twice. You could check the units, and the units won't work out if you do that. Like you'll end up with like the wrong units for your diffusion coefficient. So dimensional analysis can help guide you as well to make sure you don't make a mistake. But absolutely, you can use current density. Should be no problem.
Okay, so Adam has a series of comments, questions, but also so that yes, it will never reach the appropriate potential, but the current will also stall at a certain current. It says we were right on the money. The excitation waveform showed exactly like that. So it is a so that means
it's a compliance.
It is a compliance voltage issue.
I suspect that it's what I said before.
Yeah.
That the compliance issue is arising because there's a connection problem with one of your electrodes.
Yeah. Well, here's a question.
Right?
There's another question. I see this happen with a lot of people. Are you using an isolation tube on your counter electrode? So I've had issues where some people, because literally this issue is occurring because so there's actually a couple things you can do. Make sure that the counter electrode area is large. Like I don't know what counter electrode you're using, but you need to make sure that the area is large and it's submerged into your solution. Because it's trying to drive current in your CO2 reduction electrolysis. And if there's insufficient current occurring on the counter electrode side, right, there must be charge balance, then it's going to limit what's going to happen on the working electrode side. So, and I would make sure that there's very little things that would block the path of current between the counter and the working electrode. So without seeing your system, I can't make I can't say too much more about that, but like that's usually the things, like when it's a compliance voltage issue. But yeah, that's what I would do.
Yep.
Check those things first. All right. Tafik is asking, yes, this is exactly how can efficiency be greater than 1? I just don't know if that equation, I don't know where that equation comes from. That if like that, how is it defined?
To me, your question seems to be to expound on what you just said there. I agree with that. I don't exactly know where that comes from. And it seems to be the situation where, and correct us if we're wrong, because there may be like an explanation of this that is valid or legitimate, or I don't know where it comes from exactly, but it's like you're taking the quotient of two thermodynamic things, the Gibbs free energy and the enthalpy, and calling it an efficiency. And then by definition, an efficiency needs to be between 0 and 1. Yeah. But it's like what thermodynamically, from first principles, from just everything, implies or assumes that is an efficiency and ought to be between 0 and 1. What principles dictate that quotient ought to be between, like, is it, in other words, delta G? Yeah, delta G over delta H. Is there some phenomenon by which delta G is always magnitude less than delta H? Is that true?
They're usually for chemical reactions, they're usually all in kilojoules per mole.
Right. But it's like, is delta G always a smaller number than delta H? Because that would make the efficiency between, you know what I mean? Like go to a tabulated set of delta G and delta H. I just don't know the answer to this question.
One thing that's very peculiar or interesting. So it's the absolute value of delta H and delta G and delta H, but like the absolute value, it's like there's positive and negative, and they are. I'm just trying to think of like a good way to kind of describe it. Like delta H, we can understand conceptually as heat. Like we can understand that physically as heat. Delta G talks. It's more about spontaneity of the reaction and whether or not it happens or not. So what does it mean when we say that when delta G is greater than or less than delta H? So you're always going to have a delta H minus T delta S, right? So delta G, let's see. So if delta H and delta S are opposite signs, so let's just say delta H is negative, delta S is positive, so that that creates a delta G that's greater than delta H. That's a situation like that can happen. And then you're gonna have a situation where it's
Yeah.
greater than 1, and that's probably there's probably a lot of systems that undergo that process.
Yeah, like again, I'm just sort of taking this as a very like like
Just
we're talking
math.
about just a simple analysis of the plausibility of what you're talking about, like confusion as to why this particular quotient is greater than 1. You're assuming it is a efficiency, but like I just did a quick search, like I'm just trying to find
Mhm.
I'm not using a real like uh textbook or tabulated whatever. I'm just trying to find any example. So here's just a random snippet from
Oh,
some
yeah.
homework or whatever. But like I'm just trying to find like tabulated values of delta G and delta H, right?
Yeah.
So like here's just these are. I mean, again, I'm assuming these are correct. Like I don't know, maybe these are wrong. I'm just gonna have to assume these are correct.
Yeah.
Okay, like KNO3, delta G is less than delta H, so that fits your efficiency idea. But just like what Alex said, for potassium, aqueous potassium ions, delta G is greater than delta H. It just happens to be. Right?
Yeah.
It's like, so that would give you a greater than 1 quote unquote efficiency if you divide delta G by delta H. 282 over 251 is greater than 1. So like and then this next one's the right order, so to speak. So like
Yeah.
I just don't know how to say with certainty that delta G is always less than delta H in all cases, such that the idea that it's greater than 1 is a problem.
Yeah.
I don't know that that's accurate. I don't. Here's another just set of, I don't know. I'm looking at this live with you here, but it's like a lot of them are either the same. This is slightly higher, 394 versus 3. This one's less. This one's less. This one's higher. This one's less. I mean, I think that again, it's sort of like the problem with this assumption, like you said, Alex. It's like H minus TS. T is
Yeah.
always positive, right? It's just temperature. Okay.
Yeah.
But like
Yeah.
S can be positive or negative. So
Yeah.
it's like, and H also. So it's like the minus TS might be making it larger or more negative.
Yeah.
It's not guaranteed it's going to result in the way that you're describing. And so it's very possible. All I'll say to finish this is that we may be not thinking exactly.
Yeah.
It's been a long time, to be perfectly honest, since we were undergraduates or even graduate, students, sort of digging into the thermodynamics of these, Gibbs energy. So I might be a little ignorant and kind of forgetting some of these fundamentals. That's entirely possible. But even just, again, like I said, a quick kind of cursory look through some of these tabulated values doesn't seem to support this notion that quotient ought to be between 0 and 1. I don't know that that's accurate.
Yeah.
Just fundamentally, I think you might have some misunderstanding about that quote unquote efficiency. That's my guess.
Yeah. Yeah. I know me.
So.
Me too. Just to say, yep, electrochemistry is hard to learn. It certainly is hard to learn.
It certainly is.
It
It's hard
really
to
is.
describe. It's hard to learn. It's hard to teach.
Yeah.
I don't know why anybody does it.
Yeah. Yeah. if only things didn't require electrochemistry, but there's a lot of stuff that requires electrochemistry.
Everything would be better if we just didn't have electrochemistry,
Yeah. Yeah.
we say justifying our entire career going down the toilet.
Yeah. Yeah. That's right. Oh gosh.
Oh, that's funny. Yeah, we often have this talk with our boss who's just like, I hate electrochemistry. Let's just sell pizzas.
Yeah.
Let's just,
Let's just sell tubing.
yeah, let's just sell something else, something simpler. Our lives would be a lot less complicated, but they'd be less entertaining.
Yeah. And
You
less
know?
interesting.
If we did a Ask Us Anything About Tubing live stream, I don't think we get a lot of people to join. Ask us anything about tubing. Unless it's like tubing like on a river, or like on a lake, you know what I mean? Like,
oh yeah,
where you have a boat and you drag an inner tube across.
Yeah.
That's fun. Have you ever done that? I don't.
Wait, we had a didn't we?
Oh,
do
we did
something
that
like that
at a company
At
thing.
a company
Yeah.
summer event. That was a long time ago.
Yeah, we
That
did.
was
We
fun.
did. That's right. Yeah, I don't have a boat or I don't live on a lake, but at various times in my life had a friend
I
who
don't have
had
a tube. But yeah,
I don't even have a tube.
No, you
yeah.
have a tube.
But at various points in my life, I've known people who happen to have a family with a lake house or what have you,
Yeah.
and I've done that. It's always so fun.
Yeah. So you can ask us anything about tubing.
You can ask us
That
anything
kind
about
of tubing.
tubing, and
That's
I'll be
fun.
happy to talk about the hydrodynamic flow of the lake as you get flown out of the tube and skip across the water like a rag doll.
Yes.
It's a
it's
very
fun.
interesting topic.
Oh
goodness.
okay. So
Santiago
Santiago
has
has
a
a question. I will click it. Let's see. When scan rate are carried out in pseudocapacitors, the capacitance decays when the scan rate increases. This is associated with diffusion problems. What is the cause of these diffusion problems? Let's
Capacitance
see.
decays when the scan rate increases.
So the capacitor. Well,
I'm not familiar with this phenomenon. This is a pseudo. So
like capacitance isn't like I measured the capacitance. It was like 25 microfarads. I mean,
yeah,
and
whatever.
then I measured it again, and now it's like 20 microfarads. Is that what you mean by like the capacitance
As-
decays, or does the voltage decay, or
I mean, it sounds like they're saying for like a capacitor,
Mhm.
when you're doing, for example, let me share. Like if you're doing capacitor studies, like supercapacitors, and you do CV, and you have voltage and I do it backwards. I'm all in battery mode here.
No,
Hang on. We have current and voltage, and it's like you're doing CVs, right? And that's like, 10 millivolts per second. And then you do, faster scan rate. Okay. And that's 20 millivolts per second. I'll only draw one more, I promise. Just for the full effect, right?
yeah.
And then you have you scan faster and faster, and that window improves, and that's 30 millivolts per second. Okay. So
Santiago just said yes, but I forgot what.
What was that?
Like what was the yes?
I
Like,
think you asked
the yes to what?
that you get 25 microfarads, and then you like
And then it
calculate,
go-
and you go
again-
faster scan rate, and you get 20,
and you get 20.
something like that. So it's like, right now again, remind me, because again,
Oh.
my chromosomal
Right.
deficiency means
Current equals capacitance times dVdt.
that's what it is. Capacitance times scan rate.
Yes, times scan rate.
Okay, so this is scan rate, new sometimes, or DVDT,
Yeah,
right?
yeah.
So effectively, what we have happening here is the current response is not what it should be, because if you're solving for capacitance, right? In theory here, capacitance is equal to current divided by scan rate, right? And so you're measuring the current, like basically the 1/2 current, of each of these.
Yeah.
And so it's like, as the scan rate goes up, in theory, the current should go up at the same rate. But what I guess, so the short answer here is that I'm not really familiar with this phenomenon. That's the short answer. So I don't know exactly if I can answer as to why this diffusional parasitic whatever is happening. Pseudocapacitance is a kind of an interesting phenomenon. I'm not 100%
I don't know enough about it either.
knowledgeable about it, but I guess the key is that as if this case, it's like, you can move the question if they can't see what I'm
Oh
doing.
yeah.
As if this is your sort of your whatever, your current at one scan rate, and it's like, if I increase the scan rate, and it should be at this current, but it actually reaches like this current, or maybe it decays out, or I don't know exactly what's happening, right? But clearly there's something going on where like the diffusion or the setup of the capacitance on the surface is not occurring, or that it's self-discharging. Like, again, I don't know 100%, like when people talk about pseudo capacitance, exactly what that is physically. I think that's also a thing. I think people,
I don't know what it is
I think
physically.
for the most part, people aren't entirely sure what pseudocapacitance is physically either. I don't think people really know, right? It's sort of like something that doesn't behave like a capacitor, we call pseudocapacitance because
Yeah.
we don't, because it's kind of capacitive, but it's not ideal. And so we just
Mhm.
call it pseudocapacitance. So the problem is, most likely to answer this question about, what is the cause of these diffusion problems? It's like, we would have to know more like phenomenologically, like physically what's happening on the surface. And I'm not sure that we do, or at least I don't. Maybe someone does. Maybe
Mhm.
someone has done, like spectroscopic measurements of some kind. There might be spectrometers you can use. There might be something you can use to sort of get at what the surface is doing. I don't know. I'm spitballing here.
Yeah.
But yeah, the short answer is that I don't know really what those phenomena are causing, or really what they're doing. I don't know. Do you have any?
Yeah, I mean, the only other thing to think about is that the electrical double layer structure is changing, which can absolutely happen in an
Yeah.
electrochemistry experiment. I don't know enough, and again, I also don't know enough about pseudocapacitance. My only very limited understanding is that when you expect to get a specific capacitance value, you get much more that's not very easily explainable. Um, and there's almost no way, or at least to my knowledge, I don't know how you can differentiate if there are two capacitors like in series or in parallel. If they're adding additional capacitance, you can differentiate between pseudo and regular capacitance. But it says the example you make is correct, but if capacitance versus voltage is graphed, the behavior is reversed. If capacitance versus voltage. Wait, let me just see this. The example you made is correct. If capacitance versus voltage is graphed, which graph did you have, Neil?
I'm now just trying
just
CVs
running
with,
CVs. Uh, yeah, I'm trying. I mean, in another thing to think about is that the capacitance. So going one step, taking the integral of that equation, the capacitance, or sorry, the charge is equal to the capacitance times the voltage, right? So if the capacitance is getting lower, that means less charge is getting stored across the same volt that you're applying. So something is happening that is taking away or making it harder to store charge on that capacitor. So that's, I think, another kind of fundamental thought, to something to think about to help maybe understand this conceptually. Charge is not getting stored in some way. But yeah, I don't know enough about pseudocapacitors, and
I just don't know. Everything you said is, again, it's sort of like I have the same answer. It's like, yeah, the charge isn't getting stored, and it's like, why? I don't know the answer to that, right? I don't know phenomenon wise why. It's a good question.
Yeah.
It's an interesting.
Maybe something's degrading. I don't know. In the material.
Here's a good question that Albert Einstein can answer.
Can we create matter from energy?
E equals mc squared.
E equals mc squared.
Yes.
So yes.
So if you take your hand, it has a certain amount of mass, right? Multiply it by the speed of light squared. That's how much energy it is.
Yeah, that's true. I guess.
Yeah. Your question is like, that's like Einsteinian physics or something.
Yeah.
Yeah. That's how nuclear power works, basically. That's how nuclear power works. Like a nuclear fission reaction, like a power plant or whatever. It's Einstein, basically. Like a rod of uranium decomposes when you do this mathematics. I did this in college. Uranium.
You said like it's Einstein. It's like Einstein is in the power plant. Generating power.
Yeah, that's actually what's happening. He didn't die. He's in the power core of a nuclear power plant. Like
his brain.
Yeah. No, actually him. Like Albert Einstein, the man, like the person who's actually there. Yeah. Like the way like hamsters run in wheels and it like lights a light bulb. He's just inside, like just
thinking.
physicsing.
Yeah, physicsing.
You know, and that's what produces electricity for the world.
Yeah.
No, but when like when uranium, what is it, 238, 235, whatever the isotope is, I forget. That's that is used for like a fission reactor decomposes. It's like it basically like a neutron gets shoved into it. It's like uranium plus. It's not exactly electrochemistry. It's not exactly chemistry. It's kind of chemistry. It's like uranium.
It's radio. It's like radio.
It's radioactive
or
decay.
radioactive
But it's
decay.
like uranium, whatever 230, whatever the number is, plus like a neutron, and then it decomposes to like xenon and molybdenum, whatever the elements are. I don't know exactly. The point is when you do the energy calculation for that, like the you end up with this missing amount of energy, and that's where E equals mc squared comes from. Basically, it's like when the mass of the products should be this, like mass should be conserved,
right?
But it isn't. So it's like the mass of the products you get, like the isotope 1 plus isotope 2 is slightly less than the mass of the uranium or whatever. And that's why it produces energy, because the mass is converted directly. The missing mass is converted directly to energy. And that mass is really small. It's like a few neutrons or whatever worth of mass, right? And so the mass of a neutron, you can look it up. It's like 10 to the minus 19 kilograms or some crazy small number.
But times the speed of light squared
times 3 times 10 to the 8 squared,
you
get a measurable amount of energy, and that's a pretty large amount of energy. And that's why a nuclear reactor is tremendous at producing energy, and you boil water in a turbine, and that's how you get electricity. So anyway, we just went on a big tangent about
but we did answer,
that is
can
your
we create matter from energy.
Oh, see, actually,
so we showed
we just showed how to create energy from matter. But not the other way around.
Not the other way around. I don't know if it's a completely reversible
I don't think you can
process.
I don't think you can go the other way, unless you're like a superhero. Like I bet if like Superman uses his like laser vision,
or what is it, Dr. Manhattan from Watchmen?
Oh yeah,
he literally can do anything.
He turns anything into anything. So Dr. Manhattan from the Watchmen?
The Watchmen,
that's yeah. He can do it, but nobody else can. Next question. Okay.
Making it real.
Exactly.
Real easy for us to define potential. It doesn't.
Hand pink waving. I think these are like emojis from YouTube. They show up.
Oh yeah.
Here.
Yeah.
They don't show up here. It probably shows on YouTube. For us, this is what it comes through on Restream.
Yeah. On Restream.
So apologies for that.
Yeah. But define potential.
That's a good question.
It's a good question.
Define potential.
Yeah, I mean, I usually like go to this textbook and then just like look up the definition, but literally the definition in this textbook is like an entire chapter. Like all of chapter 2 is the definition of potential. And there are many definitions of potential, because there's definitions from electrochemistry, there's definitions from physics, and they all kind of have to mean the same thing. But usually some people have described it as a difference in free energy, sort of say. So, and that's how we can even think about it in electrochemistry as well, because literally you've probably seen Neil actually had this at the very start of this live stream. You had
I didn't do it.
You had delta G.
Oh, delta G.
Delta G is equal to NF or minus
NFE.
NFE. And so the question is like, what is this? Right? What's this thing?
Why does it have a tail?
Why does it have this little tail here? Can't have that. I can't have a tail.
You can have a tail.
You can have a tail.
Why not?
I used to have a little tail. But this is interesting because it relates the potential to the free energy. And usually when we're thinking about things like potential and doing electrochemistry, and we have something like an electrode that has a certain like energy level or kind of states, right? So we have a potential here, and then we're looking at like the HOMO-LUMO gap of some like, some orbitals or something. We move this whole thing like up and down. We're literally moving the free energy available to do reactions. So moving this up and down creates enough free energy to reduce or oxidize, a species. Actually, this should maybe go here, and this actually goes here. But that's what you're doing. Like, that's one kind of definition of potential. It's a measure of available free energy to do things. So that's at least one definition. Hopefully that kind of helps. Maybe even helps you understand electrochemistry a little bit more. But yeah, when you change the potential, you're changing the available free energy to do chemistry and reactions. That's one way to think about it. I don't know if you have anything else to add, or
I generally think of potential as, I mean, it's kind of, I don't know, it's similar to what you said. It's just the difference in states between two things. Like, to break it down as much as possible. Like as an example, what I usually use as an example to illustrate potential in like electrochemistry, like the potential between, there's no such thing as, like, nothing has a potential.
Oh, right. Yeah.
That means
yeah,
you
by
don't
itself.
have potential. You have no potential. You should quit. No, that's not what I mean. I'm kidding. Like iron doesn't have a potential. It has a potential with respect to something else. It's always, there has to be.
Yeah.
It's not an absolute quantity. It's a relative quantity, right? So that's the first thing. And then when it's like, if you're trying to conceptualize what is the potential of, X metal with respect to whatever else, it's like if I take this textbook, I can't reach it, it's over there.
Oh, you want me to give it to you?
I can't reach it.
There you go.
So if I take this textbook and I raise it up, it is above this desk, right? The potential is easy to visualize in this case. The potential energy, but potential exists in the distance between where my hand is and this book is and the table. So if I drop it, it falls and converts that potential to kinetic energy, right? And then it hits the table and it's gone.
Yeah.
But that's why it's relative. So the potential now over here, you can't see it. If it's not above the table, I'm holding it in the same place, like relative to my own body. But now it's going to fall I'm not going to drop it because I'm going to destroy something. It's going to fall all the way to the floor. So the relative reference moved from the table to the floor. So the amount of potential increased. So it's like, again, just to sort of back it to the basic definitional sort of state here, the potential is the amount of the state or the amount of energy or the amount of whatever that I can get out of something in relation to something else. So in this case, it's the amount of speed, right? Kinetic energy, whatever you want to call it, that I can get out of this book relative to the table, floor, a giant hole in the ground, the ceiling, right? With the ceiling, it's zero. I can't drop the book and have it hit the ceiling because gravity exists. So anyway, that's about as much as I can do for you there.
Yeah.
There you go.
All right, we got a couple other questions coming in. Someone is asking about, I think the next one actually has to do with power density, energy density, power density of your battery. How do you know the energy density and power density of your battery? And then kind of a follow-up is, can I convert specific capacity discharge curve to power density and energy density?
Yeah. So first of all, how can you know the energy density of your battery? Did you ask it nicely?
Yeah.
Sorry, that's just a bad dad joke. So the first answer is, to the best of my knowledge, there isn't really a difference between energy density and power density. Those are, I think, somewhat interchangeable terms. So, I'll walk you through that a little bit here. So power density is generally defined as the watt hours per density here. Okay. So this is the part where there's possibilities here. So watt hours per, and because it's density, it's either per liter, right? Or per kilogram usually. Or per, you could say, surface area, maybe, probably less likely. I'm just saying, because it's a density, it's power per something. Okay, so typically something like watt hours per volume or per mass would be what it is. Now the bottom part of this, and again, energy density is often described the same way. Okay, and then how that's calculated from like a charge discharge curve. So dimensionally, a watt is equal to an amp times a volt, right? So this is power, if you will. The unit power is equal to current times potential, just dimensionally, right? An amp times a volt is a watt. So if instead with a battery, I have amp hours, which is a capacity, it's also an energy, so it's like coulombs, times a volt, I get a watt hour. Okay, so that just dimensionally, I'm just kind of showing you where this unit comes from. So what this means is that from a discharge curve, if I have like a representative discharge curve here, this intercept down here, by the way, is the question gone? They can see.
Let me have the question. There you go.
Okay, yeah, I'm drawing stuff and maybe it's gone.
Yeah.
So
yeah.
this intercept down here, this is like a chart. There's like a discharge curve. This is either time or capacity, but let's just say you know enough to convert this to milliamp hours or amp hours, whatever. I drew amp hours up here, so I'll just keep that. Whatever this number is here, that's the capacity of your battery. So there you go. And then typically people multiply by what's called the nominal voltage, which is, it's usually just kind of like the middle of this right here. It's like, what voltage do I use, right? That's the tricky part. So typically you'll see batteries rated, for example, as like 1.5 amp hours and 3.7 volts. Usually it's like the middle of the discharge curve. That's kind of what they call the nominal voltage. So basically, if you have a discharge curve, you take some part of, now this is tricky, it's subjective. It's like I can just pick a voltage up here and I'll boost my perceived power density. So there's a bit of a trickiness exactly what voltage to pick, admittedly. But roughly speaking, it's like some median voltage times the capacity that you measure, and that would be your power or your energy density.
Nice.
I think that was it, right?
Yeah,
How do I convert? Yeah, so that's roughly how you would make that determination.
Yeah. All right. Going through the list. So I think very, very easily, what is electrochemistry? Logical computation.
I feel like we get this every week now because we say don't ask this question.
Yeah, it's okay. But we found a way to answer it very quickly, which is that electrochemistry is the union between electricity and chemistry and the study of those things. So it's whether it's taking electrical energy, converting it into chemicals, or chemical energy into electrical energy. So I don't know anything about logical computation, but that's not what electrochemistry is. So hopefully that helps. And as we kind of go through the list, in electrochemistry, light is considered a wave or a particle. So it's not just electrochemistry. Just in science, light is considered both a wave and a particle. Like there's the duality of light.
Mm-hmm.
And also electrochemistry has, only if you're doing like spectroelectrochemistry or photoelectrochemistry would you think about or consider those things. So that's the answer. It's both. And then we've been getting a lot of questions from Falsch Dino, which is about what is Ohm's law.
I can't tell if this is a serious inquiry because this person is asking 900,000 times what Ohm's law is.
Yeah, but we can. But it's simple enough to answer. Ohm's law is just I'll share it, but it's just voltage is equal to the current times the resistance. That's Ohm's law. And all it really states is like, and you can think about it, is if I had some kind of power supply, like plus and the minus, it's going across a resistor. The resistance and the current that drives across the resistor. Actually, I did this the wrong way. Usually it's like from negative to positive, but everyone kind of draws it differently if you're an engineer or not. But the current that flows, like the voltage of the battery or the power supply, and the resistance and the current are related by Ohm's law. So if you're given two of these things, you can solve for the third. But that's just a very basic relationship to understand that I can get more current to flow if I have a higher voltage and a lower resistance, right? That's one way to think about it. You can think about the resistance as the voltage over the current. And then similarly, you can think of the current as the voltage over the resistance. These are all just different ways to think about Ohm's law. But that's Ohm's law in a nutshell. So hopefully, Flash Dino, that's the answer.
Hopefully you don't have any more questions about Ohm's law,
Yeah,
because we're not talking about it. Don't ask. It's over.
yeah. You need something a little more specific. We can do that.
That's right. So Tamim has a
yes.
question: how to determine instantaneous and progressive nucleation growth by chronoamperogram.
I don't know what instantaneous and progressive nucleation growth.
I mean, I guess I
is.
don't even understand exactly. This seems a little like, I don't think I understand this question. How to determine instantaneous and progressive. So first of all, instantaneous and progressive are kind of opposites. Something happens instantaneously and then progressively. One happens over time, one happens instantaneously. Those are different phenomena. And then nucleation growth,
nucleation growth.
I don't know.
I don't
exactly
know
what
if
you're-
you can
I'm not sure what you're asking about, to be honest.
understand. Like, I understand chronoamperometry from like the very like basic understanding of like, okay, I'm oxidizing or reducing an electroactive species in solution. But are you using chronoamperometry to grow something? I mean, maybe that's what you're talking about. Are you talking about using chronoamperometry for like plating or something like that? Like, oh, I needed to like create I'm plating some metal on something using chronoamperometry by applying some potential. So there's the nucleation and then the progression of that nucleation growing by chronoamperometry. I'm not so sure that process is well understood via chronoamperometry. Normally, chronoamperometry and the equations and math that we have to describe it for like traditional 3-electrode systems, that only applies to like a diffusion controlled process, which I'm not sure that nucleation and instantaneous nucleation growth is a diffusion limited process. That's I mean, if you want, I can just talk to you about regular chronoamperometry and maybe I don't know, maybe that's helpful, but please like leave a comment if that's something that you want me to talk about, because in chronoamperometry, it's very simply we have a great understanding of Ohm's law. But in chronoamperometry, the potential that you apply as a function of time looks something like this. So first you're applying like nothing, and then you step the potential, and then you hold it. And you end up getting a current response as a function of time that looks like this. It tends to just like, it will spike up, and then it'll decay gradually over time. So, and this is current. So one thing that's very important to note in chronoamperometry is that there's some section of your current that is associated with double layer charging and capacitance and resistance that happens at the very beginning of your chronoamperogram, and then later sections actually relate to like diffusion of some species in solution, right? So this section has to do with it's called like the RC charging of the electrical double layer, and this is diffusion. So
Diffusion.
Yeah. So that's So that's like when you're, and this is defined by, and you can use the Cottrell equation for this. The Cottrell equation defines, describes the current response. So if you're, and leave a comment if you're like kind of trying to describe something or more clarification, but I don't know enough about like nucleation growth, whether or not you can understand those processes with chronoamperometry. So, but this is generally what we do or what we use when studying diffusion controlled redox species. Now, if I had to take a guess and you were plating something, right? So if you have your electrode and you're plating something on the electrode, maybe it's a diffusion controlled process to grow a layer on it. So you're trying to understand the nucleation as well as the continuous growth of this layer. Maybe chronoamperometry will be useful. But the actual, I will say, nucleation might be very difficult to understand because nucleation is probably somewhat contained in this RC beginning step region.
Yeah, let me hide the question. I just realized it's hiding half of that. There you go.
Oh, so the nucleation might be happening here. This is the initial nucleation, which is instantaneous. And if it's instantaneous, that means it's happening in this very fast region where the double layer is charging in your chronoamperometry experiment. And then all of your what was the word that you used? All of your the growth.
Yeah, nucleation or growth or something.
Yeah, progression, nucleation, growth. That will happen like here. So it's nucleation. This is just general growth, slow growth over time. So the only things that you can try to do to maybe tease out these values so you can subtract it from the current response to really understand nucleation is to do the experiment without any of the analyte here. So you would want to remove this whole stuff from your solution and then figure out, okay, what is, how high does this peak go? And that's associated with background charging. And then do it with your species. And the difference in that peak current will tell you more about the instantaneous nucleation, the current associated with instantaneous nucleation. That's a guess about what you're describing, if I had to take a guess. So hopefully that's helpful.
This next question here is one I haven't seen in a while. This is one I typically get asked a lot when I do my impedance webinars. What is the role of DC bias in EIS? I try to answer this question when people ask it in a way to make you think about why you're asking this question, which is to say, what is the role of the potential that you apply when you do cyclic voltammetry? Right? I know you're not talking back to me because I'm on YouTube and you're commenting. But if we were having a discussion and you asked me what is the role of DC, that's what I would reply. I would say, tell me what is the role of the potential when you do chronoamperometry or cyclic voltammetry or linear sweep voltammetry. And then I'll answer for you because you can't answer right now. If I said, well, okay, so you have some redox process that happens at whatever potential, like 200 millivolts. And I say, okay, well, what if you're doing an LSV? What potentials are you picking? You say, okay, I'm starting at 0 and I'm going to 400 millivolts. Why? What is the role of those potentials? Well, obviously, I'm starting at 0 because it's before I oxidized the thing, whatever, and I go to 400 because that is after I'm oxidizing it at 200, right? So I'm going to scan over the peak to see it oxidize. Okay, so good point you just made. The point here that I'm trying to make is that those kinds of thought processes that the electrochemistry researcher is having when they're determining what potentials to do DC methods at chronoamperometry or cyclic voltammetry or linear sweep, those are not different when it comes to impedance. I know impedance often feels like an alien and a different technique, and it's entirely separate and it's weird. You get imaginary numbers and all kinds of crazy things. But figuring out what potential to do impedance at involves the same line of thinking as it does when you're doing cyclic voltammetry or linear sweep or chronoamperometry. Like perhaps the better comparison would be chronoamperometry. So if you have some process that happens at 200 millivolts, like I said, versus NHE versus silver chloride, doesn't matter, 200 millivolts, and you want to generate that product, you can hold your electrode at 300 or 400, whatever. It's above that potential. That oxidation reaction, for example, will happen. And if you hold your potential there, you'll get some current associated with it, like Alex just drew with this chronoamperometry, right? Because I want to study that process that happens at 200. I have to pick a potential above 200 so that it's happening. Okay. So again, my last question to you, and I hope you answer this time, is what are you trying to study with impedance? Are you just doing impedance because your advisor told you to do it, or because there's a paper that someone said they should do it? Maybe. But fundamentally, why are you doing impedance? Are you trying to study that reaction? Is your open circuit potential above 200 millivolts such that that reaction is happening? Probably not. It's probably not physically possible for that to be the case. So then if you want to study that reaction and the impedance effects of it, probably you should pick a DC bias that is making that reaction happen, just like you would with chronoamperometry or LSV or anything else, right? This is another one of my, I talked about Tafel plots about an hour ago, and I went on a big soapbox about it. This is another one of my soapboxes. I want to get people to stop thinking that the bias of impedance is some mystical phenomenon. It's the potential that you're at your electrode is going to determine what's happening. Just whether you're doing DC or AC, it's all irrelevant. Whatever potential you're at, something will be happening. If you're at OCP, not a lot is happening, right? You don't have a lot of Faradaic reactions. You just have double layer capacitance or whatever happening. And if you apply a different potential and do impedance there, you might have a Faradaic reaction happening. So if you want to determine the charge transfer resistance of your electrode performing whatever reaction, you better be at a potential where that reaction's happening. So there you go. That's the role of the DC bias,
Yes.
basically.
Let's see. There are a couple. They seem kind of like silly questions, sort of say, but like, can we create infinite energy? The answer is no.
No,
because
you can't.
Energy is conserved. So always. Why is the anode negative and the cathode is positive in an electrochemical cell? Is that correct?
Yeah.
Okay.
Yeah.
All right.
Yeah. That's just a convention. It just comes from a convention thing. So
yeah.
That's
that answer.
No, I'll explain it a little bit, slightly more detail. Just erasing. So the convention with the terms anode and cathode typically have to do with a battery or a fuel cell. Sometimes in electrochemical cells, you'll call things anode or cathode, but it's often with respect to a battery or a fuel cell. That's the first thing. The second thing is that the battery or fuel cell, it's more obvious. A battery is trickier because a battery can be charged or discharged. A fuel cell isn't charging and discharging, but you can think about it in a similar way that when you're getting energy out of a fuel cell, it's like a discharge. Okay. So the convention related to what I just said is that fuel cells and batteries, things that use the terms anode and cathode, are definitionally defined by when the system is discharging. So with a battery, when you are discharging, there's a reduction reaction happening at the cathode and an oxidation reaction happening at the anode when you're discharging. Same with a fuel cell. With a fuel cell, when you're discharging or getting energy from it, there's a reduction reaction happening at the cathode, oxygen reduction reaction, for example, and an oxidation reaction happening at the anode. In a PEM fuel cell, that's hydrogen production. Okay. The convention, again, this is why this is all basically convention. A plus E goes to B. So a reaction is written standard as a reduction. Right? So if this is the cathode reaction, again, as it's discharging, then the anode has some reaction happening. C goes to, whatever. This B might be here too. Just forget about the letters. It's not that important. It has an oxidation happening at the anode. Okay. The E cell, the potential of the cell is defined as during discharge, again, E cathode minus E anode. Okay. So this is, if I have to posit, to be honest, I'm not 100% sure why the positive, negative, like signs are applied, but I think it's probably something like this. This is like positive and this is negative because the potential of the cells are cathode minus anode. That's definitionally how it works. And the E, right, this is again another convention of electrochemistry, is that the E0 is defined for the reduction, right? So the E, so like for a fuel cell, this is the oxygen reduction reaction, right? And so the oxygen reduction reaction, right, O2, I'm going to butcher this, plus 4 electrons, plus 4 protons, right?
Yeah.
Gives you 2 water.
Yeah.
Oh, I did it. I did it. I'm so proud of myself. Is that right?
Yeah.
Yeah. So that has an E0 written this way, and that comes from doing the Gibbs free energy of the products minus reactants, basically, of about 1.2 volts. Okay. And the anode reaction is actually just the hydrogen reaction, which has a 0. So that's why the E cell of a fuel cell, a PEM fuel cell, is 1.2 volts roughly. So that's like the theoretical amount of energy you can get out of a fuel cell. Anyway, as it relates to a battery or anything else, you would have, this cathode reaction is 1.5 volts. The anode reaction is minus 2 volts. So when you subtract that, you get 3, right? 1 minus a minus 2 is 3. So that's partly how, like, is usually very largely negative, and it's a minus a negative. And then the cathode reaction is also some positive number. And then when you subtract that, you get 3 or 4 volts. So, so anyway, that hopefully that's relatively helpful. That's just explaining of these conventions, and that's how it works, basically.
Nice. All right. So we have a question from Nandu. Why do you think companies are not adding options for online IR correction in their potentiostats? I mean, potentiostats can potentials do measure resistance during chronoamperometry. So
that's a different question.
Well, yeah, that's a different thing.
So yeah, you're I mean, you can explain it probably well, but basically you're conflating two things. The IR correction aspect of a potentiostat is much more complicated than just knowing what the resistance is. It's a whole circuitry thing, right? So,
well, yeah. So first off, there are companies that do offer online IR correction. So some potentiostats do have a feedback circuit, and so like if you have one of our potentiostats that has it enabled, so there's some electronics that go into it. But if you're looking at like a cyclic voltammetry experiment, if you go to the advanced, it's always an advanced aspect. You can turn IR compensation on or off. Like you can adjust it. So potentiostats do have the ability to have automatic IR correction. And let me just make sure. So it's and then you don't always want to have whatever the resistance is exactly added to your potentiostat. You may have to choose a lower resistance when doing IR correction because you can generate overcompensation. Like you can overcompensate for the IR correction, and that can cause problems. So usually we recommend people like manually IR correct in the sense that they measure a resistance and then they choose how much of that resistance they want to compensate for when doing an experiment. And then you can, in principle, measure the resistance using chronoamperometry, but it's not done automatically because, we don't know what electrochemical system you're working with and whether that solution resistance value is ultra accurate. There needs to be certain conditions met when doing chronoamperometry to measure the resistance. So I hope that kind of answers your question, or at least gives you some kind of inkling as to why this happens or why it doesn't happen. Okay. We're slowly running out of time, but I think there's a few small questions there. Let's see. Can E naught of a cell or delta G for a cell reaction ever be equal to 0?
Sure.
Yeah, especially if you define because E naught's with respect to something. So usually when we have an E naught value, it's with respect to like the standard hydrogen, electrode or something like that. So if you have that reaction and you're referencing that reaction, it's going to be 0. That's going to be 0.
Yeah, I mean, this is honestly one of those things that's just happenstance. Like potentials are actually, this leads into your next question as well, because it's, what does the negative sign in the expression of the basically the E0 of the zinc 2+ reduction is negative 0.76 volts. There's really no answer to that question. It means it's negative 0.76 volts. That's just what it is. And that's with respect to the hydrogen reaction. Again, potentials are with respect to two things. That's just, the answer is, it is. Thermodynamics dictates.
Well, yeah,
right?
yeah.
I don't know how else to answer this question.
Yeah, so you could have the negative sign means that the free energy for converting zinc 2+ to zinc, it's a non-spontaneous process. So you need to add energy to have that, that's what the negative sign means. But if you had a positive sign, it means it's a spontaneous process. So you could have, copper, for example, like copper oxide, has a positive voltage, which means it is a spontaneous process. And we know that because copper oxidizes just in air without any potentiostat, without applying any voltage, but we can still measure the free energy associated with it. It's a spontaneous reaction. So the sign convention has to do with, relative to whatever your reference electrode is, or the standard hydrogen electrode or something, the process is more or less spontaneous or will happen based on that sign. So it's like more like I need a lot of energy for this to happen, or it's going to release a lot of energy when those chemicals mix in a circuit. So that's what I think about when I think about the sign convention, particularly for like an E naught reaction.
Looked like Nandu had a bit of a clarification.
Yeah.
IR correction is from the predetermined value, but solution resistance evolve with time.
I think that's an assumption. I think it's assumed. It's an assumption that solution resistance is constant. I think that's just an assumption we make in electrochemistry, that the solution resistance doesn't change.
Yeah. In theory, it shouldn't either. Like unless there's some fundamental, if the solvent is being evaporated and the concentration's increasing, or you're fundamentally changing the solution, the electrolyte somehow over time, or I don't know, something else is happening, right? If it's not really actually changing, then in theory the resistance shouldn't change over time. Whether that is exactly easily measurable practically and everything is a whole different situation, of course, but in theory it shouldn't be changing.
I don't know how it would be changing.
But IR compensation is also one of those things that in some cases, if it isn't too large and affecting everything too badly, you can simply correct your data afterwards. You can correct the potential for the IR drop after the fact And again, if the amount of IR drop isn't too crazy, it's roughly equivalent to doing it live, like during the experiment, if your potentiostat has that feedback circuit in it.
Mhm.
But if it doesn't, you can do it afterwards.
Mhm.
And it can be an accepted practice.
Yeah.
Can absolute electrode potential of an electrode be measured? No, that is not a thing. There's no such thing as absolute electrode potential.
There is a thing.
There is no such thing. Potential is between two things.
No, there's a well. Talk to Dan Shearson. You need
Ugh.
to have a very long conversation with Dan Shearson
Yeah, that's your thing. I don't
because
have
there's
long
like a
conversation.
whole because you can define potential in like a vacuum or something, which is it's overly complicated. It's like extremely
But
complicated.
it still has to be with respect to something else, right? Like,
It's with respect to some kind of vacuum permittivity,
and
or
it's still with
something
respect
like
to
that.
something else, you know?
Still with respect, but it's defined as like an like the physicists want to have potential on like an absolute scale, not relative to like reference electrodes, right? So
Yeah.
that's when they call it like the absolute potential.
But even then, it's still a misnomer, because if it's with respect to vacuum, then it's the potential with respect to vacuum.
Potential with respect to
And
vacuum.
that's what you're saying, right? It's like, there's still something on the other end of that, you know,
of that thing on the
yeah,
other
like
side.
the potential, like I do not accept. I haven't had 12-hour conversations with Dan Shearson or another professor who knows a lot more than I do, granted.
50-hour
Yeah.
conversation with Dan Shearson.
But that being said, I will be hard to convince, I suppose, that at some fundamental level, microscopically, this metal surface just has a potential independent of literally everything else.
Oh, but that's what it's defining. It's literally everything else, right? It's like in a vacuum, what is the potential to move an electron from this point to that point, or something like that? There's a lot of like theoretical stuff with it. It's definitely super weird. It's like it's very abstract. It's like these textbooks are just like go into it in more detail, but it's a physics. It's like a crazy physics problem. I don't even go into that.
It's definitely beyond electrochemistry. You know, that like transcends the practicality of doing electrochemical stuff, right? It, like, really does.
Yeah. Let's see. We'll maybe just finish this. And let's see. Wait, but I don't even know if there's a question. If there is a reaction happening, it produce a product that alters the resistance, assuming that you have a current of 2 amps. Well, if you have a current of 2 amps,
then you have a
then you
tremendous
have
amount
a
of
thing
IR
like
drop
that.
for sure. Yeah, because IR drop means current times
Yeah.
resistance drop. So
Yeah.
even if your resistance is small, like 1 ohm, 2 amps times 1 ohm is 1 volt. 2 volts, excuse me. Math is hard. 2 volts.
Yeah, 2 volts.
2 volts of shift is massive. So,
but even in that situation, we're assuming that the voltage and assuming that the current and the resistance are the same. That we're assuming that it's 1 ohm and it doesn't change.
Yeah.
So, I think that, well, what you can do here's the way to kind of prove it, which is do EIS or do an uncompensated solution resistance technique to measure that thing, like positive feedback or current interrupt or something like that, at different times in the experiment, and see if you get dramatically different resistance values during the course of the experiment. You probably will. All right, I think we can't. I don't know if we can answer these other questions about molar conductivity and aqueous electrolytes. I think because it's been over 2 hours. I think we're gonna call
if you have
it
more
a day.
questions, I would suggest that you put them as a comment to the video, or you can send us an email or something like that. I'll put our email address again last time.
This question is like, which of the following plots provides the?
This sounds.
You ain't telling me what the plot is. I can't see it.
This sounds like you're just copy pasting one of these G questions or something.
Yeah, that's right.
And in which case, for one, we can try to give our, best educated guesses or work out some of these questions. But frankly, I have just, all I can tell you is that I have sympathy for you if you're dealing with the, joint entrance exams or whatever other exam questions are, in your future for grad school or postdoc or whatever it is. I know that some countries have different, levels of testing and things like that. That's what this question looks like to me. So yeah, good luck. I wish you luck. I know that's a tricky thing, for sure. We have some version of that here in the US. It depends on the university. It's not quite so, it's not the same like all the IITs in India kind of have, the entrance exam you have to do. And it's kind of whatever, standardized for the most part. If you're going to IIT Bombay or IIT Kolkata or whatever, you kind of have the same one. In the US, it's not, every university sort of does its own thing. We have different kinds of exams, but it's a little more, anyway, it's a little different. So all I can say is that I have best of luck to you. I wish you I have sympathy for you. These are hard tests. The IITs, for example, in India, as probably other countries have similar phenomena, are competitive as heck, and right, it's hard to get in. Yeah. So best of luck to you. I suppose I don't know how much more I can say in that regard. And I guess we'll wrap it up here. It's been a couple hours. So yeah. We appreciate everybody's questions today. We appreciate another successful episode, number 40.
Number 40.
It's been 40 of these. Can you believe it?
Yeah.
It's crazy.
Going strong.
I know. Well, people keep coming and asking questions. We'll keep
answering them.
Trying to answer them. I guess that's all we can tell you. So we'll see everybody next week, and have a great weekend. Take care.
Bye.